Welcome, health data explorers, to a critical mission in our machine learning journey. I'm excited to be here with you. And today we're diving into a classification task using a powerful tool from the Interpret library. I'm running this in Google Colab, breaking it down into clear code blocks so you can follow along as we investigate a data set about stroke risk. Let's start by setting up our environment and gathering our tools to get started. I begin by installing the Interpret library in Colab with pip3 install interpret. This library is our gateway to explainable AI, helping us understand our model's decisions with precision. Next, I import the essentials: pandas for data manipulation, NumPy for numerical operations, and Matplotlib's pyplot for potential visualizations, though we'll focus on Interpret's built-in plots today. From Sklearn, I bring in train test split to split our data, and F1 score and accuracy score to evaluate our model. I also import random oversampler from Mblearn to handle data imbalance. And from Interpret, I import classification tree from the Glassbox module, our star model, along with the show function to display explanations. I set up inline visualizations with set visualize provider and inline provider, ensuring our plots render directly in Colab. With our toolkit ready, let's load the data. Now, I load the dataset using pandas read_csv, pulling in the healthcare dataset stroke data.csv file from my system's datasets folder. I print dataset.head to take a look. The first row shows a 67-year-old male, hypertension 0, heart disease 1, ever married yes, work type private, residence type urban, average glucose level 228.69, BMI 36.6, smoking status formerly smoked, and stroke 1, indicating a stroke. The next row shows a 61-year-old female, average glucose level 202.21, BMI NAN, stroke 1. This dataset, often used in health analytics, contains 5,110 records of patients, with features like age, gender, health conditions, lifestyle factors, and a binary target, stroke, where 1 means a stroke occurred, 0 means it didn't. It's a real-world dataset aimed at predicting stroke risk, but the target is imbalanced, with only 249 stroke cases, about 4.87%, as we'll see later. Let's pre-process it. I check for missing values with dataset.isna.sum. ID, gender, age, hypertension, heart disease, ever married, work type, residence type, average glucose level, smoking status, and stroke all have 0 missing values, but BMI has 201, about 3.9% of the rows. Next, I drop the ID column since it's just an identifier and not useful for prediction, using dataset.drop with axis 1 and in place true. To handle the missing BMI values, I calculate the mean BMI, 28.89, 3237, and fill the nans with this average using FILNA. This ensures we don't lose data while keeping BMI realistic. I print dataset.info to get general information. 5,110 entries, 11 columns. Gender, ever married, work type, residence type, and smoking status are objects, categorical. Age, average glucose level, and BMI are floats. Hypertension, heart disease, and stroke are integers. Memory usage is 439.3 kilobytes. Nice and manageable. I dive deeper with dataset.describe for statistical insights. Age ranges from 0.08 to 82, mean 43.23, median 45, patients span all ages. Hypertension and heart disease are binary, with means 0.097 and 0.054. About 9.7% and 5.4% have these conditions. Average glucose level ranges from 55.12 to 271.74, mean 106.15, median 91.89, some high values indicating potential diabetes. BMI ranges from 10.3 to 97.6, mean 28.89, median 28.4. After filling nans, it's slightly skewed. Strokes mean is 0.0487, confirming only 4.87% of patients had a stroke, highlighting the imbalance. This statistical snapshot shows a diverse patient group, with age, glucose levels, and BMI likely key for predicting stroke risk. Let's encode the categorical features next. Identify the categorical columns: gender, ever married, work type, residence type, and smoking status, using select types with include object, storing them in categorical columns. I apply one-hot encoding with pd.getDummies, creating binary columns for each category, prefixed with the column names, and cast to integers for consistency. I concatenate these encoded columns with the dataset and drop the original categorical columns. The updated head shows the result. Gender female 0, gender male 1, ever married yes 1, work type private 1, smoking status formerly smoked 1, age 67, average glucose level 228.69, BMI 36.6, stroke 1. The dataset now has 22 columns, all numeric, ready for modeling. This encoding ensures our model can handle categorical data without ordinal assumptions, capturing patterns like ever married yes versus smoking status smokes and stroke prediction. With the data pre-processed, I split it into features and target. X is all columns except the last stroke, and Y is the stroke column. I use train test split to allocate 20% for testing and 80% for training, with random state 2021, giving us 4,088 training samples and 1022 test samples. Given the stroke imbalance, only 4.87% positive, I apply oversampling to the training set using random oversampler with sampling strategy minority. I convert XTrain and YTrain to NumPy arrays, oversample to balance the minority class, stroke 1, and convert back to pandas data frames and series. This ensures our model isn't biased toward the majority class, stroke 0, improving its ability to detect stroke cases. We're ready to train our classification tree. I initialize the classification tree from Interpret's Glassbox module, a model designed for interpretability, splitting features to minimize impurity while offering clear explanations, unlike Sklern's decision trees. I call fit on XTrain and YTrain to train the model, and it prints training finished. I make predictions on XTest with predict, storing them in YPred, and evaluate with F1 score, macro average, and accuracy. The results: F1 score 0.4867, a moderate balance of precision and recall across classes, but low due to the imbalance challenge. Accuracy is 0.9481 to 94.81% correct predictions, but likely skewed toward the majority class, stroke 0. With only 50 stroke cases in the test set, the model struggles to catch them, favoring the 95% non-stroke majority. Let's explore its decisions with explainability. I start with the local explanation for the first 100 test samples, calling tree.explainLocal on XTest slice 0 to 100 YTest slice 0 to 100, name tree, and displaying it with show. The plot shows predictions for each sample. For instance, sample 0 has actual 0, predicted 0, with a probability score of 0.8339, confident in no stroke. The tree path mirrors the global structure we'll see next. Age less than or equal to 67.50. Ever married no less than or equal to 0.50. Average glucose level less than or equal to 231.49. And hypertension less than or equal to 0.50 lead to a no-stroke prediction. Features like age and glucose levels contribute most, with impurities, e.g., 0.47 at hypertension less than or equal to 0.50, showing where splits refine the prediction. This local view highlights why the model predicts no stroke for this patient. Age and glucose levels align with lower risk, despite potential risk factors like smoking. Now, I move to the global explanation with tree.explainGlobal, displayed with show. The plot reveals the tree's overall structure. The root splits on age less than or equal to 67.50, with 0 observations on both sides, indicating a perfect split, impurity 0.0. If age is less than 67.50, it branches to age less than or equal to 55.50, impurity 0.00 observations. Then age less than or equal to 44.50, impurity 0.01, 0 observations. Younger patients are less likely to have stroke. On the right, Age greater than 67.50 leads to ever married no less than or equal to 0.50. Impurity 0.00 observations. Then average glucose level less than or equal to 106.42. Impurity 0.22 observations. Versus less than or equal to 231.49. Impurity 0.27 observations. Deeper splits like hypertension less than or equal to 0.50. Impurity 0.47 observations. Refined stroke risk. Impurities like 0.27 at average glucose level less than or equal to 231.49 show where the tree reduced variance most. Age, glucose levels, and hypertension dominate. Key indicators of stroke risk. Let's reflect on these outputs. They're a health checkup for our model. The head showed a 67-year-old male, average glucose level 228.69, BMI 36.6, stroke 1. High risk, correctly in the dataset. Missing BMI values, 201, were filled with a mean 28.89, ensuring no data loss. The info confirmed 5,110 entries, with categorical columns like gender and smoking status encoded into 22 numeric features. Gender male 1, smoking status formerly smoked 1. Statistical insights revealed ages mean 43.23, max 82, and strokes mean 0.0487. Only 4.87% positive cases. F1 score 0.4867 reflects the challenge of detecting strokes, while accuracy 0.9481 is high but skewed. The global plot's age less than or equal to 67.50 split shows older patients like our head's 67-year-old are at higher risk, with average glucose level less than or equal to 231.49, 228.69 fits, and hypertension less than or equal to 0.50 fits, refining the path. The local explanation's prediction of no stroke for a sample, actual 0, predicted 0, probability 0.8339, aligns with these features. Age and glucose levels drive decisions, but the model misses some strokes due to imbalance. To wrap up this vital investigation, we've analyzed the stroke dataset, a critical collection of 5,110 patients, and trained a classification tree, achieving an F1 score of 0.4867 and accuracy of 0.9481. Oversampling addressed the imbalance, but stroke detection remains challenging. The global explanation highlighted age, glucose levels, and hypertension as key predictors, with splits like age less than or equal to 67.50 setting the stage, while the local view showed how individual predictions, like a no-stroke call, rely on these features. Classification tree's transparency gives us that XAI flavor, revealing the why behind each prediction. Grab this code, tweak this sampling strategy, and explore stroke risk further. I'm inspired by this health-focused dive. Hope it's got you thinking about data's impact on well-being. See you next time for another life-changing analysis.